Good afternoon and welcome everyone. My name is Sierra Lamonaco and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the program lead for the Skule Lunch Learn. Thank you for being here with us today for our very special Skule Lunch Learn presentation. With alumni tuning in from all over the world, we have guests joining us from 6 different countries, including Canada, England, Hong Kong, Iran, Israel, and the United States. So welcome. Now, before we start today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are grateful to have the opportunity to work on this land. Now, I hope each and every one of you are very excited for today's presentation because I know I am, especially since one of our speakers is someone who is extremely dedicated to inspiring scholarship that is focused on creating technologies that promote the safety and well-being of not only the planet, but its people as well. Margaret Chapman's current research is an excellent example of how U of T's commitment through the Defy Gravity campaign aims to enable healthy lives and create a sustainable future for generations to come. Now, a quick housekeeping item. At the end of today's presentation, we will have time for a formal Q&A session. Should you have any questions for Professor Margaret Chapman, please submit the questions using the Q&A feature below. For the individuals who submitted the questions during the registration period, I want to say thank you. Thank you for pursuing your curiosities and sharing your insightful questions with us. We have shared your questions with the professor before today's presentation and will continue to share any questions that we receive at the end. Now, without further ado, it brings me great pleasure to introduce the one and only MC and Chair of the Skule Lunch Learn program, Laurie Hevola. Laurie is not only an Electrical 65 grad, he is also one of our most dedicated and engaged members of our alumni community. Laurie has been chairing the Skule Lunch Learn program for several years, actually maybe 10 or maybe more than that, and continues to generously dedicate his time to maintaining our Lunch and Learn's long-established traditions. Now, with that, please join me in welcoming Laurie Hevola, who will now introduce our guest speaker for today's event. Thank you.
Thank you, Sierra, for your very warm introduction. It is indeed my pleasure to welcome our guest speaker, Professor Margaret Chapman. Today, she will be discussing how theory and engineering together can confront the challenges of managing uncertainty in both nature and medicine. Margaret Chapman joined the Edward S. Rogers Senior Department of Electrical and Computer Engineering here at U of T in July of 2020 as an assistant professor. Her research focuses on risk-aware stochastic control theory with an emphasis on safety and applications in healthcare and sustainable cities, both of which subjects are very timely. She earned her Bachelor of Science degree with distinction and a Master of Science degree in Mechanical Engineering from Stanford University in 2012 and 2014, respectively. She earned her PhD degree in Electrical Engineering and Computer Sciences from the University of California, Berkeley in May of 2020. In 2021, Margaret received the Leon O. Chow Award at UC Berkeley for outstanding achievement in nonlinear science from her doctoral alma mater. In addition, she is a recipient of a U.S. National Science Foundation Graduate Research Fellowship in 2014, a Berkeley Fellowship for Graduate Study in 2014, and a Stanford University Term in Engineering Stochastic Award in 2012. And now, without further ado, please join me in welcoming Professor Margaret Chapman.
Thank you, Laurie and Sierra, for your kind introduction. I'm delighted to be here. I'm going to share my screen now. So thanks everyone for joining. I'm really excited to present my talk today. So these are pictures that I've taken of the Toronto waterfront near Hyde Park. And I've always enjoyed being around nature, and my enjoyment of nature has influenced my research interests, which are in the intersection of math, engineering, and nature. So a common theme of my research is discovering how to design engineering systems to help manage natural phenomena. And to do this, I use a mathematical engineering field called stochastic control theory. Stochastic control theory is essentially the theory of noisy systems. And I consider the protection of nature, which includes both the planet and human life, to be one of the most important problems that engineers can help solve. And so now the goal of protecting nature is very broad. So far, I focused my interests on designing algorithms that are inspired by two application areas so far. And so these include urban water infrastructure systems and cancer treatment. So at first glance, these applications seem very different. So water systems are typically very large. They can span hundreds of kilometers, whereas cancer systems are on the molecular scale. And also the behavior of water systems are governed by physical water flow equations and chemical water quality equations, whereas the behavior of cancer systems are governed by biological and molecular interactions and also by the chemistry of drugs. But these applications have important similarities too, and so let's talk about them. So both of these applications are affected by uncertain inputs. So water systems are affected by hard to predict weather patterns. Cancer systems are affected by patient-specific differences and also by biological noise. And we also need both of these systems to operate safely despite uncertainty. We need water systems to help alleviate flooding, and also we need water systems to help maintain good water quality. In the case of a hydroelectric dam, we need the system to store enough water so that enough energy can be generated when the water is released. And we also need the system to alleviate flooding at the same time. We need cancer systems to help eradicate cancer over time, but without causing adverse side effects for the patient. So due to the similarities between these applications, we can model them within a common framework of stochastic control. So what does this mean? So a stochastic control framework has two parts. There's a model, which we call a stochastic control system, and there's a random variable, which I'm going to denote by the symbol y. So in the model represents the underlying physics, chemistry, or biology of the system. And there's a state variable, xt, that evolves over time. There's a control input ut that we would like to design. And there's a disturbance input wt that is uncontrollable. And so the state xt, the control input ut, and the disturbance wt, they lead to the next state xt plus 1 through the function f. And the random variable y, it represents an uncertain outcome that we'd like to optimize. So let's look at some examples of y. So in the case of a hydroelectric dam, y could represent the random volume of water that's released into an emergency spillway during the next storm. And so we'd like y to be as small whenever possible, because we only want to use the emergency spillway when absolutely necessary. And so let's look at an example from a different application domain next. So in the case of the leukemia treatment system, y could represent the random concentration of mature neutrophils at a future time. So neutrophils are a type of white blood cells that are in all our bodies, and they're needed to support a healthy immune system. So according to the treatment protocol at the Princess Margaret Cancer Center in Toronto, neutrophils should be within a range from 1 to 2 10 to the 9th cells per liter, 10 to the 9th cells per liter of blood. And we also know that low concentrations of neutrophils are very harmful because we need enough neutrophils to support a healthy immune system. So this figure shows a a model of a leukemia treatment system that was developed in 2020. And there are two parts. One part describes the kinetics of a drug called 6MP, of a chemotherapy. And the second part describes how the neutrophils mature over time. And the neutrophils, they mature in the bone marrow. And this process is affected by the drug. And we can only regularly measure mature neutrophils, but the neutrophils at the preliminary stages of maturity, we can't easily measure them. So overall, my research is about designing algorithms to analyze and optimize systems that are affected by noise. So what is analysis? So analysis means we'd like to understand how the system behaves in different situations. And to optimize a system means that we'd like to help the system behave better. That is, we'd like to help the system behave more safely and more efficiently. And so noise refers to an uncertain input, which we call a disturbance. So let's look at some examples. So for a water system, a common disturbance are the different rates of precipitation. For a cancer treatment system, disturbances could be differences between patients with the same diagnosis. So even if a patient has the same disease, they can still respond differently to different treatments. Okay, so there are two mainstream paradigms that have emerged in the literature for managing a system's behavior under uncertainty. And these are called the worst case paradigm and the risk neutral paradigm. So the worst case paradigm quantifies safety or performance by assuming the so-called worst circumstances. So in this case, the disturbances behave as adversarial inputs. In contrast, in the risk neutral paradigm, this quantifies safety or performance in terms of the probability of an event or in terms of the average value of a random variable. And so the literature that I've listed, this comes from many different communities, so including machine learning, robust control theory, stochastic control theory, and formal verification. And researchers in these communities are in all different departments, so computer science, electrical engineering, mechanical engineering, management science, industrial engineering. But ultimately, you can classify most of this literature in these two distinct categories. Okay, so it's very common in practice to try to optimize the average outcome of a random variable. But this type of optimization can be quite limiting. And this is because the average ignores other characteristics of distributions. So here I've shown 6 different probability distributions. So on the horizontal axis are the possible values of a random variable. And the area under the curve in each of these distributions is 1. So in all cases, the average value of the random variable is 0. But these distributions have very different characteristics. So 4 of them are symmetric, but their tails have different shapes. And then there are 2 distributions that are asymmetric, where one has a heavier upper tail and the other has a heavier lower tail. So in applications where safety is important, we care about providing protection against rare harmful outcomes. And these are the outcomes that would show up in the upper tail of a probability distribution. So in contrast to the existing standard paradigms, I am interested in the design of risk-aware algorithms. So these algorithms are aware of a spectrum of possibilities between the average outcome and the very worst case outcome. So here I've shown the density of a random variable y, and I've indicated the average outcome. But then we can consider different worst cases where a quite harmful outcome would appear in the very right-hand side of the horizontal axis. So there's a very strong motivation for studying risk-aware algorithms, and one is that the expected value or the estimate of the worst outcome do provide a limited view of the spectrum of possible system behavior. So I would say that these other 2 paradigms, they oversimplify the possible circumstances that could arise. And also in practice, systems require an awareness of rare harmful outcomes without being overly cautious. And I've depicted three very different applications. One is civil and environmental infrastructure under weather uncertainty. So for example, water systems, and then also electricity systems that are affected by renewable energy sources, which are quite uncertain. And then there's cancer treatment systems, which are affected by patient-to-patient variabilities. And another application are transportation systems, which can involve both autonomous and also human-driven components. So the design of risk-aware algorithms is quite interesting, but it's also very challenging, and it's very important. And the challenges basically reduces to the fact that it's very difficult to predict and characterize rare events. But we really need to provide protection against rare events because unfortunately they're going to happen and the consequences can be catastrophic. So I'd like to spend some time providing a brief history of this interesting research area. So the origins come from the idea that two people can have different perspectives about the same outcome. So for example, two different people can view $5 in very different ways. And in the academic literature, this first appeared in a paper by Bernoulli, which was written in Latin in 1738. A function that quantifies an individual's particular perspective is called a utility function. And the optimization of exponential utility functions for control systems have been studied since the early 1970s, so for the past around 50 years. And the first paper was by Howard and Matheson in 1972. And to date, most risk-aware algorithms involve the optimization of exponential utility functions. And so here are some example papers. So the first researcher to bring this into the control systems community was Jacobson in 1973, and he considered the special case of linear control systems subject to where they would like to minimize quadratic costs and where the noise is assumed to be normally distributed. And this type of problem or this type of setting is called linear exponential quadratic Gaussian, or LEQG. And then in the 1980s and 1990s, Peter Whittle and his colleagues solved the LEQG problem in the setting of partially observable states. So this means that they designed controllers without direct access to the state, but instead they need to use noisy measurements to design the controller. And then later research has focused on more general settings. So for example, where the system is not linear and instead is nonlinear, which is a much larger class of systems. So there are some additional ways to measure the risk of a random variable instead of using the exponential utility function. And these are depicted, some of these ways are depicted in this illustration. So I've first drawn a hexagon, which represents the conditional value at risk of a random variable y at a given level alpha. And I've abbreviated conditional value at risk by CVaR, so CVaR. The conditional value at risk at level alpha represents the average outcome in the alpha fraction of the worst cases. So there's a density drawn for a random variable y, and the area of the shaded region is alpha, which is any number between 0 and 1. And so the CVaR represents the average associated with the gray region. And it's related to a quantity called the value at risk, or VAR, which is the best outcome in the alpha fraction of the worst cases. And this is represented by the diamond. And then the other risk measures that I've drawn are different ways to measure the dispersion of a random variable with respect to the mean. So the square represents the sum of the expectation and a quantity called the upper semi-deviation, which is the amount that a random variable exceeds its mean. And the triangle represents the sum of the expectation and the standard deviation. So these examples, I've only drawn 4 of them, but they illustrate several ways to characterize the features of a distribution. And so we may be interested in optimizing different features of a probability distribution to meet the needs of different applications. And so I'd like to present some interesting applications next. So for example, if you're interested in regulating the temperature of an office building, you might assume that deviations above and below the reference temperature are equally undesirable. So in this case, you might consider some different risk measures, which include a sum of the mean and variance. You might consider the exponential utility, which is typically interpreted as an approximation of the mean and variance. Or you might consider a sum of the mean and the standard deviation. So in contrast, if you're interested in managing overflows in water systems or hydroelectric dams, in this case, large overflows are typically much worse than small overflows. And so to deal with this situation, you might be interested in using the conditional value at risk or another risk measure, for example, the mean upper semi-deviation. And similarly, if you're interested in managing neutrophil concentrations for a leukemia patient, in this case, the low concentrations of neutrophils are much worse than high concentrations. And so you might also be interested in using conditional value at risk or mean upper semi-deviation rather than, for example, mean variance. And so basically, in order to meet application-specific needs about managing uncertainty, it's desirable to have a broad collection of tools to assess different characteristics of distributions. And so the diversity of applications is one motivation for studying risk-aware algorithms. And so let's continue to look at the history. So there's quantile-based algorithms involving quantile-based risk measures. So for example, the conditional value at risk and the value at risk are gaining popularity due to their interpretability. And so most papers focus on the optimization of cumulative costs. So these are when you optimize the sum of a random variable. And most solution methods are based on dynamic programming. And recently, there have been more applications to robot motion planning. So for example, I've listed a paper from 2021 that applies CVaR to a robot motion planning problem. I'm also writing a paper currently with some other researchers from Caltech, and the paper focuses on the applications of risk measures for robots more generally. So in addition, there are risk measures with a type of recursive structure. So this looks a little scary, where we're looking at compositions of risk measures. But this type of recursive structure, it's more difficult to interpret, but it's very useful because many algorithms have a recursive structure. So if you encode this type of risk measure in your algorithm, you can easily encode a sense of risk awareness in your algorithm. And there are also interesting works that optimize an expected sum of costs subject to a risk or a probabilistic constraint. So I really just touched the surface on this interesting research area, and a more detailed history can be found in a paper that I wrote with one of my students, Yuang Wang. And this was published only a couple of months ago, but it pretty much provides a brief history of the research area of risk-averse autonomous systems. So this is just a list of some recent publications that I've led or supervised about the theory of risk-aware algorithms. And the first 3 papers that I've listed are with my current master's students, Evan, Yuang, and Chuaning. And It has been and continues to be a joy to work with them. I think that some are in the audience today. And next, I'd like to discuss a core problem that's studied in some of these publications. And so the problem that I'll discuss is studied in the publications that are highlighted in blue. So we've designed algorithms that optimize the conditional value at risk of a random variable at a given level alpha for a control system. So we're optimizing essentially is the average value of a random variable in a given fraction of the worst cases. And so the key idea here is that CVaR can be tuned between the risk neutral and worst cases in a way that focuses on the upper tail of a probability distribution using the parameter alpha. In our work, we've considered different settings, and these include finite time horizons, also infinite time horizons, and we've also developed a guaranteed approximation method. But the key novelty in this work is drawing the connection between the conditional value at risk measure, which comes from finance, and the problem of analyzing the safety of control systems. So we've designed algorithms that minimize the conditional value at risk, which is the average value of y in a given fraction of the worst cases, where we're considering a maximum of random variables and the dynamics equations of a control system. And so this problem is very difficult because it involves optimizing the upper tail of a probability distribution. That is where the rare events are. And so to overcome this challenge, we've combined techniques that come from control theory, which of course is developed by the control systems community. We've used techniques from risk analysis, which comes from financial engineering, economics, and also operations research. And of course, we use probability theory as well, which comes from mathematics. And so I'd like to provide an illustration of the problem that we've solved. So our problem, it characterizes safety by assessing both the probability and the severity of the potential consequences of the system's behavior. So in the gray cloud, what I've shown is a family of possible trajectories of a system from a given initial condition X. And there's a random variable that's associated with the family of trajectories. This random variable represents the maximum distance between a trajectory and a desired operating region. So the desired operating region is K, which is illustrated in the green box. And so we would like trajectories to be inside K, but sometimes they might leave K. So for example, in the case of flooding, sometimes flooding happens. And so our problem is designed to minimize the average value of this maximum random variable in a given fraction of the worst cases. And so we've drawn two contours. So inside a contour depicts the set of initial states from which the risk of the random variable can be reduced to a threshold R. And so we have two different methods. One method is a guaranteed under approximation method. And this provides the pink contour, which is faster to compute, but it is an approximation. And the second method provides an exact solution, and this is depicted using the blue contour, and this is more computationally expensive. So let's provide a numerical example next. So here I consider two tanks that are connected by a valve or a pump, and the water flows into the tanks from the street due to a storm. And the states of the system are the water elevations in the tanks. The control input is either the position of the valve or it's the pumping rate, depending upon which actuator you choose. And the disturbance is the rate at which the water flows in from the street, and this comes from precipitation. And then water can be released into a storm sewer, which is the preferred outcome, or it can be released into a combined sewer, which is to be avoided. The outlets of the combined sewer are indicated by the red circles. So we would like to avoid releases into the combined sewer because then the water can flow directly into a natural water body without treatment. And this can harm local ecosystems. So we'd like to avoid the discharges into the combined sewer. And so to quantify this, we define Y, our random variable, to be the maximum random water elevation that discharges into the combined sewer over time. And so we've used this tool to analyze 4 different designs, but I'm going to show the results of 2 different designs next. So here, each row of plots pertains to a particular design. The top is the baseline design in which the actuator is a valve, and the bottom is the design where the only difference is that we've replaced the valve by a pump. And so inside the contours are the sets of initial conditions. So these are the sets of initial water elevations in the tank from which the risk can be reduced to a required threshold R. And there are 5 different columns, and these different columns correspond to the different levels, different values of alpha. And so as alpha gets smaller, so as we go from left to right, the sets get smaller too. And this is because smaller alpha means that we are considering more rare and harmful events. And so a key takeaway here is that by tuning alpha, we can get a sense of the system's behavior on a spectrum between the average and a more worst case perspective. And in particular, alpha is both interpretable and it's flexible. And so this may be useful for assessing trade-offs between system performance and financial considerations in practice, especially for applications such as stormwater infrastructure that are typically paid for by taxpayer money. So while we've developed algorithms to solve this problem, which are very hard, and the solutions are mathematically elegant, there are practical challenges. And so actually, these practical challenges are shared by most existing risk-aware algorithms to date. And so there are 2 main challenges, and these include adaptability and scalability. So adaptability refers to what if the model changes, or what if the model is misspecified, or what if your assumption about your disturbance distribution changes. And so one approach to improving the adaptability challenge is to use techniques that allow you to optimize a family of probability distributions for disturbances. And this is called distributionally robust optimization. And I've worked on this with my collaborator, Laurent Lessard. The other challenge is scalability. So this means how do we make our algorithms work for very large systems? So these are systems with many interacting components. So such as a very large water network with many nodes, such as the water network that serves the city of Toronto. And so we're working on the scalability challenge as well. And I'd like to just highlight one approach that we've used for this next, which is done with my master's students, Evan and Ewing. So we've explored a topic called extreme value theory. So extreme value theory comes from statistics, and it's the study of the long-term behavior of normalized maxima of random variables. And extreme value theory is used in hydrology for flood prediction. It's also used for earthquake prediction, and it's also used to study human longevity. And so what we found that it's useful for estimating risk in applications where there's not much data. And so what we did is we proposed an estimator for the upper semi-deviation, which again is the average amount that a random variable exceeds its mean in a fraction of the worst cases. And in experiments, we illustrated how well this estimator can extrapolate using only a small number of IID samples. And so the key idea when you're using extreme value theory for risk estimation is extreme value theory provides a model for the upper tail of your probability distribution. And it's quite convenient that this model is very simple. It only has 4 parameters. And because there's only 4 parameters, you can fit this model with a small number of samples. And so what we did is we used extreme value theory and we used data samples to fit a model for the upper tail. And in our experiments, we considered 6 different probability distributions, and we found that our estimator, which is based on this theory from statistics called extreme value theory, does better than a standard one when there are small numbers of samples. So the standard estimator is based on sample averaging and is not designed to deal with rare events. But our estimator is designed for rare events, and it can also do this with a small number of samples. And this is very exciting because many important application domains that are related to environmental and human health have small numbers of samples. So in particular, if you want to understand how a given patient is doing, or you want to measure the water quality in Lake Ontario last month, those are applications with a small number of samples. And we also know that machine learning tools typically only work well in settings with large data sets. So extreme value theory from statistics, when you combine that with control theory, this provides an avenue to overcome the challenges of small data applications. So to conclude the talk, I'd like to present some ongoing directions that we're working on and also some future ideas. So in particular, I'll talk about extensions to large-scale water and water energy systems. I'll also talk about some of the ongoing work that we're doing with leukemia treatment, and I'll talk about future ideas related to transportation systems. So this is an example of a large-scale water network, and this is a map from 1985 of the main water distribution lines in Toronto. And so we can imagine that the city's sewer system today is on a similar scale, and it may even be larger than this one. And so in the future, I envision a future sewer system that has sensors to sense different inflows coming in, and also actuators that can work together to redistribute wastewater and stormwater when necessary in order to limit overflows and also improve water quality. So this is kind of like a smart sewer system, and I'm writing a grant about this currently. And so it's kind of like a sewer system with equipped with an Internet of Things like feature, where there are sensors to sense incoming flows, and also then the actuators are coordinated, and they work together to redistribute flows to areas with capacity downstream. And they also have potential to hold back water when possible in order to improve water quality. And so ultimately, we need systems that can better adapt to large storms and to extreme storm events. And so a system that helps reduce overflows in this way and helps improve water quality could help reduce damage to the city's infrastructure systems and also support a healthier lake ecosystem by being adaptive to extreme weather patterns. But of course, before we can do this, we need to have more scalable, risk-aware algorithms to accommodate the vast size of water systems. So another approach that we are pursuing to help improve the scalability issue is to develop algorithms that are based on approximate dynamic programming, where we pay particular attention to making the algorithms rigorous from a theoretical point of view. And so this is work that my master's student, Evan, is currently pursuing for his thesis. So in addition to Internet of Things smart water systems, we also envision the application of risk-aware algorithms for multi-reservoir hydroelectric planning. So this means that we imagine the network consists of many connected reservoirs, and some of these reservoirs provide storage for hydroelectric dams. And the challenge is to balance the trade-offs between storing enough water to generate enough electricity when it's needed, but also not storing too much water because you don't want to have flooding. And so Evan's example that he's developing is actually on a multi-reservoir, it's on a multi-reservoir system. So another direction that I'm very interested in pursuing, and that I'm actually currently pursuing, is related to leukemia treatment. So I worked on breast cancer systems with collaborators at the Oregon Health and Science University for several years. And when I joined U of T, I switched to leukemia treatment. And so this is because in leukemia, patient data is collected more frequently. Because when patients come in to see the doctor, they get a blood, they have a blood sample that's drawn, and the measurements, the concentration of neutrophils from this blood sample are used to then adjust the drug dose. And so we are trying to figure out how to better adjust the dose of a drug. And currently what's done is the strategies are rather reactive. So based on the patient's measurement right now, the drug is either increased or decreased by 20%. But this reactive strategy can unfortunately lead to low neutrophil counts. And remember, neutrophils are a type of white blood cell. And then when you have low neutrophil counts, then you need to delay treatment in order to allow for time for the neutrophils to come back, which is really not good. It's a difficult situation to deal with. And so we believe that an anticipative strategy, so this is a strategy that uses a patient-specific model to optimize drug doses over time, has potential to improve patient outcomes. So this type of strategy would look ahead into the future and then use the future predictions to then determine what the drug doses should be. And so we're in the process of developing anticipative strategies using control theory. And so this is a plot that shows a simulation of a desired trajectory of mature neutrophils. And so this uses the JOST model from 2020. And we also show a simulation that's in the response to a preliminary controller that it aims to track the desired trajectory. So this preliminary controller is based on a linearized model and a Kalman filter. We use the Kalman filter because we can't observe the neutrophils at all stages of maturity. So we need to estimate what the neutrophils are, even though we can't measure them directly. And so this simulation was developed by two of my summer research students, Jimmy and Sam. Jimmy is now a first-year PhD student in California. He might be in the audience today. And Sam is a fourth-year undergraduate student at the University of Toronto. So of course, this controller is preliminary. We developed it over the summer. It does appear to track the trajectory quite well, which is rather promising. And so in the future, I envision a technology that provides optimized drug doses for leukemia patients based on patient-specific models. And then the doctor would then decide which drug doses to prescribe, whether they want to use the Kalman filter-based drug doses or whether they want to use the reactive drug doses that are based on the standard protocol. So lastly, I'd like to talk about another application that I believe is well suited to a risk-aware viewpoint, and this is the problem of ensuring safe, efficient, and sustainable transportation. So there are many different types of transportation systems, and they all interact with one another. We have public transit systems, public buses and streetcars. We have bike share. We have private vehicles. We have human-driven on-demand vehicles like Uber, and we're possibly going to have autonomous on-demand vehicles as well. And so these transportation systems are very different, and they're also funded in different ways, so both public and private, but they all share the common goals of safety, efficiency, and sustainability. And so overall, we need the entire system to be optimized to provide protection against rare events, but we also need to reach our individual destinations. So I believe that designing transportation systems of the future in an intentional, risk-aware manner could help promote a healthier and more sustainable society. So I'd like to thank, for this research, I'd like to thank my research group and my summer students, Evan, Yuang, Chuaning, Jimmy, and Sam, who are wonderful, wonderful people to work with. I'd also like to thank my collaborators, Kevin Smith, who is with OptiRTC, which is a smart technology company in Boston. He's also with Tufts University. My collaborator, Dr. Stephen Chan, who's with the Princess Margaret Cancer Center and the University of Toronto. Professor Laurent Lessard, who's with Northeastern University in Boston, and Dr. Michael Faust, who's at Princeton University. And I greatly appreciate research funding provided by the NSERC, Natural Sciences and Engineering Research Council of Canada Discovery Grants Program, and also their fantastic undergraduate summer research award program. And of course, I would like to thank my department, Electrical and Computer Engineering, for their wonderful support as well. So I would like to, this work all builds on, the work of many others. And so I'd just like to briefly go through my references. And I'd just like to highlight that this one, Hager in 1994, this is the first time that analysis of risk showed up in the reinforcement learning literature. So it was done in 1994, which I think is quite interesting. And I'm happy to share the slides for anyone who wants to see the references in more detail later on. So I'd like to thank everybody for listening to my talk, and I'm happy to answer any questions and have any follow-up discussions.
Thank you, Margaret. I was a little concerned for those, as Sierra mentioned in her opening remarks, if you do have questions, please put them in the Q&A, not the chat, the Q&A at the bottom of your screen. And just a few minutes ago, we got our first question, which is rather lengthy, and it regards your work on sewer systems. Have you engaged with the City of Toronto for the latest information about the sewer network, i.e. more recent than 85? As he points out, significant changes have been and are being made to mitigate overflows and impacts due to surface flooding in the Don Valley, for example. On the same topic, what sewer system characteristics are considered as part of the stochastic modeling? For example, the pipe material, infiltration, outflow, cross connections, etc.
Yeah, that's a wonderful question. So yeah, the City of Toronto is doing some really amazing things right now. So they have very large construction projects in various different locations where they're investing substantial financial resources and basically expanding the sizes of tunnels. So they're focusing now on basically enlarging the sewer tunnels in various locations, which is of course needed, and that's very important. So what I advocate for is, in combination with upgrading the sewer infrastructure, which the city is currently doing, is also incorporating an adaptive methodology. So these types of adaptive sewer systems are being installed in various locations in New York City and New Jersey, in particular to help mitigate overflows in the Hudson River, which is unfortunately polluted. And actually, if you incorporate adaptive technology, that can save the city money. So there's a company in Boston that installs these so-called smart sewer systems in various in various locations. And the way they make money is because cities save money, because you don't have to make the infrastructure so big if you also incorporate adaptive technology. And so, but of course, in order to innovate technology, we also need to build on what's already done. So I fully applaud the City of Toronto with their current efforts with upgrading the sewer infrastructure. And it's a difficult problem because the city keeps expanding, which of course is wonderful. And with expanding cities, we get more pavement, which means we get more urban, more stormwater runoff, which means that the contaminants from the city streets then go into the stormwater. And then if you have large storms, then sometimes view of large storms, then stormwater and wastewater is then released into Lake Ontario without any treatment. So it's a multidisciplinary problem that requires lots of different approaches. And I think that adaptive control technology has a place there. And I'm currently writing a grant for this. And so it's just a small grant to start. But I hope to, move the technology forward. And actually so I'll be submitting that in a couple of, actually by December 1st. And then in the question about where the stochasticity is. So when I view sewer networks, I view the stochasticity primarily in terms of the precipitation inflow. So of course, there's always uncertainty in, modeling the different pipes and all these other things, but I typically would view the topology of the network as being somewhat fixed. Maybe there's some unknown parts. So maybe there's certain parts that are not well mapped. There are other parts of the system that are well mapped. But I view typically the stochasticity coming from the not from a storm, that because weather is highly variable and it's quite difficult to predict. And so when the disturbance like WT, that would represent the inflow rate of the surface runoff. So like meters cubed per second of the surface runoff coming, entering the system at various locations.
Thank you. The next question I'm going to take from those that were submitted in the pre-registration. If you are dealing with deep or true uncertainty, for example, unknown unknowns, are there any theoretically, quote, better approaches?
Yeah, that's a really nice question. So I think first, more research has to be done to better understand how unknown the unknowns are. So, we can't apply fancy math or fancy algorithms to things if we don't understand the underlying system enough. So I think before designing an algorithm to help improve the operation and the efficiency of a system, we do need to understand that system by working with domain specialists and by, studying the system in the lab and doing kind of more characterization to better understand which uncertainties really need to be incorporated and modeled versus which ones we actually don't have to worry about. So I think an important aspect of applying any kind of mathematical algorithm is really understanding the domain that you're working in and understanding the context and working with domain specialists to better understand what the sources of the uncertainty are.
Thank you. We are nearing the top of the hour. So at this point, we're going to conclude. Thank you, first of all, for all the questions from our audience today. We weren't able to address them all. I'm sure that Professor Chapman would be willing to address them one-on-one because she does know who the questions did come from. We obviously would like to thank Professor Margaret Chapman for being with us today. Thank you all for such an informative and entertaining presentation on risk-aware control theory for sustainable cities and healthcare, both of which you touched on. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. A link to our online survey is being made available in the chat and will be shared with all of you by email after this event. A link to the presentation will also be shared with all registered guests early next week. Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. However, for the month of December, our next Skule Lunch and Learn event will be on Wednesday, December 7th, featuring Professor Giselle Azimi. For more information about Skule Lunch and Learn presentations, please visit the engineering website. We would also like to acknowledge and thank TD Insurance and Manulife, who are sponsors of Skule Lunch and Learn through U of T's Pillar Sponsorship Program. If you are interested in learning more about Skule Lunch and Learn series, please contact the alumni office at events at engineering.utoronto.ca. In closing, we would like to thank all of you for joining us for today's presentation, and I hereby adjourn today's session of Skule Lunch and Learn. Have a wonderful rest of your day or evening, wherever you may be in this world, and I look forward to seeing each of you again next month. Thank you.